So the purpose of the U substitution is to get it to fit one of our integral formulas with which we are familiar. So let me see if I can show you some of those. Okay, so here are the basic rules of integration that we're using in this class. First of all, we have a power rule where if you integrate x to the n, you add 1 to the exponent and divide by it. Second of all, we have the integral of e to the x, which is just e to the x. And thirdly, if we have the power x to the negative 1, you can't use the power rule because then that would result in division by 0. But it turns out that the integral of 1 over x, or x to the negative 1, is actually natural log of x, as long as you put an absolute value around the x. And then in general, if you have a coefficient constant being multiplied by a function inside of an integral, you can bring it out front. But if you have two functions being added or subtracted inside the integral, you can break it apart and just deal with each one separately. So ideally, the functions would fit one of these top three forms, or be a constant multiple or a sum of one of these top three forms. But that doesn't always happen. So looking at this example here, it doesn't fit any of those forms. And so what we look for is we look to replace the variable z with a new variable u. That's why we often refer to it as U substitution. And when we do that, we do it in such a way to make it fit one of those forms. So what might we let u equal? Well, here's some tips on what to let u equal. Let me just shrink this just a little bit. Okay. All right, so in an integral like, say, this one here, you have a quantity being raised to a power. In order to avoid having to multiply that out 18 times, what we're going to do instead is let u equal the quantity being raised to the power. So u is equal to x plus 10 in that case would be a good thing to try. We're not 100% guaranteed it'll work, and there may be different things you can try, but that would be a good thing to try. In an integral like this one, where we have a denominator, we'll often try letting u equal the quantity in the denominator. In an integral involving a natural log, oftentimes we'll let u be the argument inside the logarithm, the quantity or argument of the log. And then in an integral that looks more like this one over here, we have an exponential function, then we often let u equal the quantity in the exponent. So keeping those things in mind, let's try a few problems. So here we have the integral. Let me zoom in just a little bit. We have the integral of 2z dz over the cubed root of z squared plus 1. Now this doesn't look like a quantity raised to a power, but it actually is. Remember, any roots, when we're talking about derivatives or integrals, it's more convenient to think of roots as powers. And the cube root is actually the 1/3 power. So this would be z squared plus 1 to the 1/3 power. And so I'm going to use the tip that said let u be the quantity being raised to the power, and we'll see if it works. So how do we see if it works? Well, the idea with the u substitution is you pick your u, in this case z squared plus 1, and then you find your du, your derivative of u, with respect to whatever the variable is, in this case z. In this case, the derivative of z squared is 2z, derivative of 1 is just 0. But we don't actually want du dz in our integral. We want all variable u. So we move the dz over to the other side. This is called the differential, du equals 2z dz. And what we do is we now look at our integral to see if we have our differential du in there. This is going to be kind of determining whether this technique will work or not. And you'll notice that du is equal to 2z dz, and we do have a 2z dz there. So that's convenient. So let's go ahead and replace the 2z dz with du. And in the denominator, instead of having z squared plus 1 to the 1/3, we're going to give that its nickname u to the 1/3. And now we're almost in a form that we can integrate. We don't want to have this denominator. We're going to think of it as a power in the numerator. So I'm going to make it a negative exponent up top rather than a positive in the denominator. So we have the integral of u to the negative 1/3 du. So this fits the power rule of integration. So we're going to add 1 to the exponent and divide by it. When I do that, I'm actually applying the integral, finding the antiderivative. So I don't need to write the integral symbol, this elongated s, anymore. And the du is tied to that symbol, so I don't need to write that anymore. I apply the rule and I get u to the positive 2/3, because negative 1/3 plus 1 is positive 2/3, divided by 2/3, and then you always say plus c, because the idea of integration is we're looking for the original function that would have resulted in a derivative that was this integrand. And so it could be a plus 5, it could be a plus pi, any constant. If we were to take the derivative and get back to the original integral, would disappear. So we get a whole family of functions. Now division by a fraction is the same as multiplying by its reciprocal. So this would be 3/2 u to the 2/3 plus c. But we don't want u's in our answer. Our original question was about z. So let's see what this tells us about z. 3/2 times, and we have z squared plus 1 to the 2/3 plus c. All right, so that is one example of us using a u substitution to get our integral into a format that we could actually integrate right here. And then going ahead and applying our integral rules and putting back in the original variable. All right, let's look at another one here. Remember, when you're watching this as a video, you can always pause, rewind. So if I go too fast, you can look at it again. You can also type comments and questions in about the video. Okay, so here's another one. Once again, it has a radical in it. When you have a radical, you want to think of it as a power. So immediately rewrite it as the integral of x cubed plus x squared to the 1/2 power times 3x squared plus 2x dx. Now, once again, we don't have a product rule or a chain rule for integration. So when we see that we have this product of a quantity to a power going on, let's go ahead and try letting u be the quantity raised to the power, which in this case is x cubed plus x squared. If that doesn't work, we can always try letting u be something else. Okay, now we're going to find our differential, which is just du, which, by the way, always has a little dx on the end of it, or whatever the variable is, d that. Okay, so then in this case, the derivative of the differential du, I'm just referring to the derivative, but with a dx on the end. So the derivative of x cubed plus x squared is going to be 3x squared plus 2x, using the power rule on each term. Bring the power up front, subtract 1 from it. And then we want to look in our integral and see if that appears there, and it does. So that's good. So that means we can go ahead and make the u substitution. So we're going to have the integral of, we just gave this quantity x cubed plus x squared the name u, so it's going to be u to the 1/2 times du. And that fits our power rule of integration beautifully. So we're just going to add 1 to the exponent, which would be u to the 3/2, and divide by it. Okay. Okay. Sorry about that. All right. So, and then plus c. So division by a fraction, you just flip it over and multiply. So that's going to be 2/3 u to the 3/2 plus c. But we don't want u's. We want our original x's back. So what was u equal to? It was x cubed plus x squared. So it's going to be 2/3 x cubed plus x squared to the 3/2 plus c. Okay, let's do one more. All right, so do you see a quantity raised to a power in this integral? It's the integral of x plus 1 over, let me zoom in a little bit more, x plus 1 over x squared plus 2x plus 2 quantity to the 3rd power dx. So again, we don't have a quotient rule for integration. So when you see it looks like something that if you were taking the derivative you'd need a quotient rule, you definitely need to try using your u substitution. So we're going to say u equals the quantity inside the parentheses, x squared plus 2x plus 2. And let's see if that works. And what I mean by that is we're going to find our du. So du is nothing but the derivative of this polynomial, but with a dx tacked on the end. So this is going to be 2x plus 2 and then dx. Okay, now we look to see if our du differential is actually in the function. But it's not. But don't worry, that's okay. Because in fact, if you factor out the 2 here, 2 times x plus 1 dx, you can see that the x plus 1 dx that we're looking for is in the problem. We just have an extra 2. Now that might seem like, well, when we don't have the du that we need, but in fact, remember that we can bring constants in and out of integrals. So what I'm going to do is I'm going to put a constant multiple in front of the x plus 1, a factor of 2. So I've essentially multiplied the integral by 2, which I don't want to do because I don't want to double the integral. I want to have the same integral in the end, same value in the end that I started with. So to compensate, I'm going to multiply by 1/2 on the outside. 1/2 times 2 is just 1, and we can always multiply by 1 without actually changing the value of the expression. So we're going to do that, and now we have our differential du, 2 times x plus 1 dx. Now, important note about this, you cannot do this with an x. Like I couldn't put an x on the inside and a 1 over x on the outside of the integral. This only works for actual numbers, not for variables. Okay? Okay. But anyway, as long as it only differs by a coefficient, by a constant multiple, you can do this little trick and it'll work. So we're going to say 1/2 the integral, and we're going to have du over, and then we're going to have u to the 3rd power, and now we're going to change that to a form that we know how to integrate. We're going to put the u into the numerator by changing the sign of its exponent. So we have u to the -3rd du. So now we can use the power rule of integration. So that's going to be 1/2 we're going to remember when we apply the integration rule, the integral symbol and the du, those are together, those are linked. So once we integrate, those go away. And then we just have u to the negative 3 plus 1 is negative 2 over negative 2. And then always the plus c. So the integral symbol and the du go away and the plus c appears there. All right, now let's go ahead and simplify a bit. So that's going to be, let's see, negative 1 over 4u squared. If you multiply the 2 times the negative 2 and move the negative exponent down, I don't like to leave a negative exponent in my solution. And then also we need to go back to the x's that we had to begin with. So this is going to be negative 1 over 4 times x squared plus 2x plus 2. And then we're going to have to the second power plus c. Okay, I hope you found this video helpful. If you did, please remember to give it a thumbs up. That'll help other students to find the video. And remember, if you're one of my students, to post a comment with your name or alias, the day and time of your class, and a quotation from the video in order to get some bonus points.